So how many of you could not get Arduino yet? So is it on the way? How many of you get the set, or how many of you get set with LEDs? Okay, so we can give you a homework with LEDs, right? Yeah. The problem with the lab homework was your assistant prepared it. It is supposed to be pre-lab homework, but they were confused and they actually put the lab inside. So I'm gonna make it simpler and more theoretical. Okay, theoretical, to submit before the lab, because it is for the preparation of the lab, not the lab itself. So they put the lab itself, which could be a little bit more difficult, but the problem is, the issue is, pre-lab homeworks are given for you to get prepared, not to do the lab. Okay? So I'm going to replace it with an easier one after the class. You may need to resubmit. If you have already submitted, you may need to redo it. So today, our topic is a little more interesting. We will be talking about the computer architecture, the general computer architecture, and we will be introducing the machine language. I have uploaded a VizMachine simulator file yesterday. Some of you may have seen in the class Teams page. When you download it, and you can run it on your machine as an HTML file, as a script. We will be talking about how the CPU works. We will be introducing the VizMachine and the program. For about 2 weeks, we will be focusing on the assembly language given in VizMachine. But the VizMachine is a theoretical simulation, not real CPU. It is so simple. It is for teaching. But if you know it, you can understand all the other CPUs. And if you work in embedded systems, if you will work in embedded systems in future, which is very important and high-paying job, then that will help. But we are teaching it to everybody because we want you to understand how things work under the hood. Very big company owners sent their son and daughters to starting level jobs in their factories. Okay? So that when they become executive, they will understand how the factory work is. It could be 1 year, it could be 6 months, but they will learn how it is. So this is similar. It is not for using in the future, but it is for teaching what it is. Short-term military is also similar. Bedelli askerlik kind of military is, to me, is not good. It has to be 1 month. It has to be 1 month, and also you should pay. No problem. You should pay the cost because you understand how war is, how fight is, what the weapon is, what the situation is like, so that when you become politician, having the military service done at least 1 month, you will understand the costs, the human costs associated with it. Otherwise, you will say, let's go get the Syria, for example. So it could be an easy saying if you don't know how to do it on the floor. So this is what it is. Enough talk. So we have the central processing unit, CPU. We will have arithmetic logic unit and control unit. We have registers. And to connect all of them, we will have bus. So let's see how they are. We have an arithmetic logic unit. This is the general content. Arithmetic logic unit, control unit, some registers, some memory. That's it. So there is no magic. There is nothing additional that Americans implemented or Japanese or Chinese implemented and works magically. This is what it is, okay? And you can make it. So arithmetic logic unit is made up of gates. We have covered that little bit in the last week's section. It was like this. It had two inputs, A and B, and output. So depending on what you input from A and B, the results will be immediately displayed because it's made up of gates. When you have a gate, AND gate, how does it work? You provide 0 here, 1 here, and you get, this is an AND gate, you get 0 here. How long does it take? It's almost instantaneous. Almost, not exactly. So it is very, very, very, very fast. Therefore, it is not related to clock cycle. So it is very fast, instantaneous, but with some delay. Because in the transistors, you have 5 or 6 transistors here, for example. In the transistors, there is a capacitive effect, and that capacitive effect should be fulfilled for some time in order to stabilize it. So in order to get it stabilized, it takes some time, but it is in nanoseconds range. So typically it can be negligible, but it is not negligible when you are designing a CPU in high speed like gigahertz range, because in gigahertz range those delays add up and could be significant and limit the CPU maximum clock cycle. Like when you are buying a CPU with 3 gigahertz, it will be more expensive than the CPU with 2 gigahertz because the construction and all the materials and technology will be different to improve that, to reduce that delays so that the frequency can be increased. So we have arithmetic logic unit. We have arithmetic logic unit, control unit, and registers, many registers. Usually in this one, you might have 16 registers. In some CPUs, you may have 2 registers. In some others, 32 registers, 64 registers, powers of 2 sometimes 5. So it depends how you implement it. There are many different processors, like ARM processors, Intel processors, like Apple Silicon processors, or simpler processors like ESP32 or Arduino processors, right? So this VizMachine is VizMachine is the implementation of the Brookshire machine. The guy from Austria wrote a nice simulator. Its name is VizMachine, and it can be downloaded. And I also zipped it and put it in our class folder so that you can download and use it. It's very nice. It's a hypothetical machine. It goes with the assembly language given in the book. And the description of the machine is given in the appendix. Efendim. Dersteyim ben ama hızlıca söylerseniz. Geçerli. Tamam, bay bay. So it's not real machine. It is in the appendix. So this is the structure of our Brookshire machine or VizMachine. We have an arithmetic logic. These are like blocks. In reality, it is a circuit. Arithmetic logic unit block, control unit block. You have registers. How many registers you have? 16. But in hexadecimal standard, it's up to F. Register 0 to register F. F is equal to what in decimal? Sorry? Huh? F is 15, not 16, because you start from 0. So from 0 to F, and you have the instruction register, and you have the program counter. It is connected to the bus, to the main memory. Main memory also has cells that are 8 bits. Each of them is 8-bit. So 8-bit, right? To 16 by 6, no, not 16 by 6.
It's 15.
1, 2, 3, 4, 5, 6, 7. I made it wrong, so the main memory is 250. 256 bytes. You write your program here and execute. You write your program in binary numbers, in hexadecimal numbers, and it is possible to execute it. These are the instructions, commands that the machine can understand. It is like load. But if you have a question, please ask. Load, store, move, add. We don't have subtract. Or, and, XOR, rotate, jump. Jump means go to in any kind of program. And halt. We have halt is stop. And we have wait and write extended instructions for the VizMachine implementation for doing much interesting things. This is the circuit. How does it run? What do you think? How does it execute? How does it move? The idea is, it is fed by a clock. How many of you know hand-cranked meat grinder? Kıyma makinesini biliyor musunuz? Elle çalıştırılan. Beyaz alüminyumdan, demirden. Masanın kenarına alttan sıkıştırılır. Böyle çevirirsiniz. Buradan eti koyarsınız. Buradan et alabiliyorsanız.
Mengene gibi bir şey mi hocam? Masanın altında.
Masa tutturması öyledir genelde. Klasik. Eski teknoloji çünkü. 1920'lerden falan beri aynı hali. You hand crank and there is a spiral which is Archimedes spiral. So it moves the stuff to the front, right? And there is a cutter in front, it goes. So you hand crank one by one. Similarly, we have a clock here. You crank it, you crank the system, and it moves. At each crank, this instruction is understood, whatever there is, it is understood and implemented by the control unit, by the supervision of the control unit, and operations are done on registers through arithmetic logic unit. Either add or XOR or negate or whatever. In the complex CPUs, you have multiply, extended multiply, extended move, mathematical functions like sine, cosine, etc. So all of the instructions can be like this. But in order for teaching, this is only what you have. You don't even have subtraction. Yeah.
Loadların farkı ne?
He?
Loadların farkı ne?
Bir tanesi 5 adresindeki sayıyı yükler. Diğeri 5 yükler. Birçok instruction'ın böyle varyasyonları vardır şeyde. Kodları farklıdır. Mesela bunun kodu 1. Aslında bu X'te load ama bu 1, bu da 2. Başka bir instruction yani. Kıyma makinesi gibi tık tık tık tık. So that's clock. And at each turn, this is increased. And this program counter at the beginning shows here. After one turn, it shows here. Another turn, it shows here. Another turn, it shows here. So program moves at each turn of the clock. And at each turn, this content is taken into the instruction register, understood, and executed one by one. This movement is also controlled by closing and opening gates. If you open the gates connected to here, it is closed. How you select which cell is connected to the bus? There is a mechanism called address decoding. It's also a gate-based thing. It's a complex gate. At each different number coming from this address, it is the address bus, different cell is selected automatically. So that is determined by the program counter. When program counter says 7, it means the 7th element is going to be read. When I say jump 15, when I say jump 15, program counter changed to 15. So 15th, where is the 15? I don't know. 15th element is then the next instruction. So I can jump somewhere else in the code by changing the program counter. Okay, any questions? Yeah.
So it stores output on main memory.
It stores output at the main memory, as you say. There is a store. If you run that instruction, register value is taken back to the memory. What I said was program execution. It was program counter. Program counter is different. Data is different. In von Neumann machine, program and data are both in the same memory. When you have a program, the modern any kind of program, data plus code is here. So some of the numbers are code, some of the numbers are data. For example, when you have an image, for example, image may take this block. Obviously, this is how many pixels? 1, 2, 3, 4, 5, 6, 7, 8 pixel image. But in reality, it is much larger. So a block contains the image or the text. But other parts is the code. So they coexist, and the program counter shows in which part of the code I am interested at the moment in meat grinder. Because after one turn, it will be the next automatically, unless I say go to somewhere else, based on the condition of some internal register, which is the implementation of if statement. If this is equal to that, then go to here. So that will be done by checking a variable and jumping accordingly. And the associated instruction is jump to the instruction in memory cell with the address XY, this, if the data register in R is equal to the data register 0. So there is a checking mechanism. If they are equal, then jump. So using that, I can implement an if-go structure, which is available in any computer language, because branching is a must. A program can be encoded, I will come to that again. A program can be encoded as bit patterns and stored in main memory. From there, the CPU can extract the instructions and execute them. In turn, the program to be executed and can be altered easily. So the program will be in the memory, because we can read, write you can play with it. You can write another program. You can put your data. So it is basically now. It could be different, but it's basically a RAM if you can read write. If you can, and random access, you can access to anywhere, not sequential. You can go here, then here, then here, anywhere you want. It means random access. If you can read write, which is the case here, it is RAM. If you can only read, it is going to be wrong. Read only memory. So these commands are machine instructions. So think about, you are developing a communication mechanism with your friend who lives in the other apartment. All you can do is saying 1, 2, 3, 5 with hands. So when you say 1, it means come here. Let's go and have a tea. 2, I'm coming to you. 3, let's go shopping. 8, because that is the only thing you can see from window to window, right? 8, so it means my father came, so let's not do anything. So these are 15 instructions. Not even 15, 12. So those are the machine instructions. They might have the name, such as one is, what was it? Come here. Come here. So instruction itself is the 1. But the name of it is come here. That name eventually can be written as a language. Come here, let's go. If there is no, check the kitchen. If there is nothing to eat, then let's go to outside to eat something else. So that kind of programming can be done. And you can give names to the actions rather than numbers, because writing with numbers can be confusing. 1, 2, 3. You can memorize it during communication, but during planning, it might be a little confusing. So therefore, it is converted into assembly language. The machine language are 1, 2, 3, 4, 5 made up of instructions. But names of those instructions leads us to a programming language which is called assembly language. We check those names, convert them to numbers, then it turns into machine language, which is, these are assembly instructions. Okay, those are assembly instructions. These are machine, the left is machine instructions. So machine can only understand these, but the human can use this part. But on the machine, it is in this form. In the exam, please don't give me answers with these instructions. I cannot read it. If I ask you to write an assembly language program that does something as an exam question, use assembly language, not machine language. Is that clear? I can't read binary. Well, I can, but that is not the purpose. So with, how many of you heard the word risk? Yeah. RISC means reduced instruction set computing processor. CISC is complex instruction set computing. In the RISC architecture, like Apple Silicon, IBM, Motorola, these are having less number of instructions, such as 150 instructions. Less means not 10 or 15. Less means in the industrial case, 150 is a small number. Complex instruction set computer is like 300, 400 instructions, sometimes 500 instructions for everything, for every complex thing. When you have small number of instructions, complex operations can be implemented by more steps. But the hypothesis is many things can be implemented with less number of steps, and with the small chip size, because chip size becomes smaller, heat dissipation reduces, power dissipation reduces, you can go higher in the clock cycle, and also you can be more efficient. That means if you make the chip bigger, it will be more efficient. So reduced instruction set computing is relatively powerful, I think, to me. And also, when you are writing compilers, for example, you have languages. Tell me about the languages that you know. What languages you heard about?
C#, Python,
Yeah. What?
JavaScript.
Yeah. What else?
What else? A little bit C++.
Rust. C++, C, Pascal, Go,
Kotlin.
Kotlin. That's JavaScript. Huh? Yeah. COBOL, PL1, Fortran, right?
Scala.
So all those languages are going to be translated into these instructions. Come here, let's go out, etc. So that machine language instructions should be extracted from those languages. And we call that process is compiling, compilers. Right? In Turkish it is derleyici. So compilers are the programs that translate those languages, instructions in those languages, to machine code. There are also interpreters, which are languages like BASIC, Python, Lua. How many of you played Roblox? Not much. Why didn't? So Roblox allows you to implement your own environment, and it has a programming language built in, so it is very good opportunity for high school students to learn programming. Unfortunately, it is forbidden in our country, and for various different reasons. For high schools, it is also regarded as a bad thing because people play game part of it, but there is a coding part of it as well. So you can develop your own code, own interactions, which is very powerful. And we had a TÜBİTAK project. With a company that uses Lua as a platform for teaching programming languages to high school students, because most high school students are not interested in programming. There is some interest in programming in middle school, right? But those interest is only due to the popularity propaganda by the private schools, to say that our kids are learning programming, blah, blah, blah, but they stop doing it in high school. So if they are really interested, if they are really serious, the private schools or fancies, etc., if they are really interested, they should teach programming in high school rather than middle school. And Lua language is a good, much better language for teaching than Perl or Python. Those languages, Basic, Perl, Python, Lua, those languages are interpreted languages. C, C sharp, Pascal, Rust, those are compiled languages. The compiler creates a machine code file, and that file is loaded into memory, and it is executed from the machine language. On the other hand, interpreted languages like Perl, Python, Lua, Basic, Lisp, those languages are translated line by line when you are running your program. One line is translated, executed. The second line is translated, executed. So there is an interpreter running all the time. There is an interpreter running all the time that translates human readable language to machine language at each line. For the compiler, it is done once, and it is never done again during runtime, during execution. Do you understand the difference? So for those reasons, generally speaking, those interpreted languages are much slower, like 50 times slower than compiled languages. For example, Python is like around 50 times slower than counterpart C language, the same program. Okay? It could be convenient, but it's slow. Also, with the compiled languages, checking is more rigorous. Checking is more advanced. So errors can be caught in earlier stages before running your program. On the other hand, interpreted languages create errors if there is a problem in the code during execution. You don't know before it happens. So that is the difference. I wouldn't say don't use it, but it is different. So the machine instruction types: come here, let's go to shopping, give me some money, whatever. So those instructions are generally three types. One is the data transfer, second one is the arithmetic logic, third is the control for the CPU, not for the neighbor communication. Even with the neighbor communication, some instructions are hi, hello kind of instruction. Some instructions are let's go in type of instruction. So you may classify them as well. So this classification is for CPU, and data transfer between memory and registers, arithmetic logic add two registers and put the result in the third register. So it is arithmetic operation or logic operation. Then the control instruction. If this and go to there, or stop, or wait. So how does it work? The meat grinder, get in the step 1, get one of the values from the values to be added from memory and place it in the register. Step 2, get the other value. This is an A plus B equals to C program. Well, actually, we write it in the computer domain. C is equal to A plus B. Not A plus B is equal to C. In mathematics, when I say A plus B is equal to C, that refers to equality. They're always equal. But in computer, no, it's different. C is actually computed by adding A plus B. So it's not equality. They are not always equal. Actually, they are not equal. You are just assigning it. For that reason, in some languages, like for example in APL, the notation was different. This was the notation because the scientists, the designers of that language said equality is too mathematical. So we are not talking about equality here. It is an assignment, right? There is no equality. So keep in mind that in computer programming, equal sign doesn't mean equal. It is assignment. If you are going to check against equality, some languages use EQ, AEQ, if AEQ B. So checking against equality. Some languages use EQ. Some other many other languages, A double equals. So are they equal? And for example, y equals mx plus b. So this shows me what it shows me what?
Y is mx plus b.
In mathematics.
Equation
Equation for the line, right? It's an equation for the line. So it represents a line. But in computer programming, it doesn't represent anything. It may be related to the computation of something with the line, but it doesn't represent the line because equal sign is not there for equality representation. It is for the assignment. In Pascal language, C is equal to A plus B. So colon plus equal is used for that purpose. Hani elleri varmamış diyorsun ya. Equal kullanmaya elleri varmamış. Bu değil diyor. Bunlar eşit değil diyor. Ben assign ediyorum diyor. Bunu buna yüklüyorum diyor. Tamam mı? Bu hatayı her yıl ilk başlarda midterm'de falan içinizden bir %5 yapıyor. Bunu lütfen yapmayın. Bu bir eşitlik değil. So C is equal to A plus B. Get the first number, get the second number, add them through the control register and arithmetic logic unit, put the result to the third register, and store the result back in memory somewhere else, and stop. This is the simple program. So when we try to move to assembly language, it will be associated as, no, this is another example. get the number 1, get the number 2. If the second value is 0, it can't be divided. Make a division and store the register back. So there is some if condition here. So basically, we have registers in the Whiz machine, in the Brookshire machine, but it is the same in other Apple chips as well. So just numbers are greater, number of instructions are greater. It's more complex, 32-bit, 64-bit. So it is harder to teach as 101 class. The program counter will start from 0, 0. So this cell, if I crank it, kıyma makinesini buraya koyalım. If I crank it 1, and this cell will be loaded into here. Understood and executed. In the next crank, this will be taken in, understood, executed. Unless you say something like this, jump to step 6. This jump actually changes the program counter to something else. So it is associated with jump. It goes somewhere else and continues from there. Do you understand? These instructions are here. Some instructions are multiple bytes, longer instructions. Some of them are shorter. These are 8-bit in this VizMachine. Today it is 8-bit generally. The memory is shown as the collection of 8-bit cells. In 1950s, 1960s, maybe early 1970s, they said, no, our memory is made up of words, not bytes. Sometimes the word is 23 bits. 23 bits. Okay? Why is that so? Because what they say is, first, are you following me? First, 8-bit is for instruction. For 8-bit is for instruction. Another, kaç kaldı geriye? Another 10-bit is for data, and another 5-bit is for additional information. And if you give this, the control unit takes it, okay, this is what I have to do, this is the data, and these are the other things that I have to consider when I am doing it. So all the things are given in one line. They call it word. And the CPU was executing word by word. Today, we don't pay attention to that. The architecture is standardized. So we say 8-bit, 16-bit, 32-bit, 64-bit, right? But it is all multiples of 8. So some instructions are 32-bit instructions. They are always 32-bit instructions or 64-bit instructions. But in the memory, we don't represent it word by word. If it is 32-bit architecture, we have 4 of them. So 4 of them is one piece. Okay? 4 of them is one piece. The Whiz Machine has 16-bit. So we have 2 by 2. 2 by 2 by 2 by 2. This part, what to do part, was the opcode. The rest was the operand. Add 2. So 2 is the data, add is the instruction. Add 2, right? Or add memory location 57. So memory location 57 is the operand. Add is the opcode. So part of the machine instruction, first part, usually the first part is the opcode, second part is the operand. It is various, there are various forms, but generally this is opcode and operand. So this Brookshire machine online is available on, you can say VizMachine, but this turned into German, so I loaded into Teams. You can use it from your laptop locally. It had 16-bit words. Wow, big stuff. 16-bit words. First 8-bit is what to do. From window to window. Come here, let's go to dinner, etc. So the first part is the how many maximum instructions you can have? 16. At most 16 instructions. You don't even have 16, it's like 15 or 13. The rest, let's go to dinner to the kebabchi at corner. So you are describing which, where, and what. Okay? So this is the action, and these are the objects connected to the action. Türkçesine bu yüklem, bunlar da nesne. Değil mi? Usually, this Whiz machine is constructed by this 5 indicates register number. This A7 is the target address. Or source address. Such as load the number at location A7 to register 5. This says, I think it's store. Store register 5 to A7. Is that clear? Store register 5 to A7. What was 3? Let's check. Yeah, 3 was store. 3, that 3, store. In the exam, I will give this sheet, this part. So you don't need to memorize, but you will memorize eventually because there is only 15. There are only 15 instructions. On the other hand, we have so many things to do in this class, so I'm not gonna do this forever. It is only for a couple of weeks. Then we will keep it as a question for the exam. That's it. You will be on your own. So this 3 means store, 5 means a register, A7 means the address. It's one piece of word. In the older days, they say word, but today, yeah, people use it, but that's the instruction. So the program I was talking about at the beginning, this program, this program, adding 2 numbers, can be, with that kind of notation, can be encoded as like this: 1560, 1660, well, I wouldn't say 15, 1560, 1660, 505, 5056, 306E, C000. So this 1 means what? Load, right? Another load to the register 5, load to the register 5, which address? 6C. So 6C goes into register 5. 6D goes into register 6. Register 5 and register 6 are added, and the result will be put into register 0, which is the add. If I say 5156, the result will be put into register 1. But this program, as he wishes, puts the result into register 0. So it is up to me to change it. Is that clear? Then store the register 0 to location 6E and stop. Because if you don't stop, VizMachine keeps going and it will start to execute the other addresses, which could be garbage. So terminating the program is important. It doesn't stop.
But in exam, we are not going to use the numbers.
No, please no. In the exam, you will use, well, you should design the program that way. You will use these.
So we don't need to know the numbers, which numbers.
Well, you don't need to know, but you will eventually learn because there are few of them. Because you will be doing homework with the VizMachine, and you will be seeing it. So you don't have to memorize it, but you know it.
For reading the machine, we need the numbers.
What was that?
For reading the machine.
You are not going to read the machine.
Okay.
You are going to work with the machine, and you don't need the numbers, but it shows what number it is. You select. It is very easy. You select, because there are 15. Each command, each instruction is selected as a pull-down menu. So you select instructions from pull-down menu. So everything is done with the pull-down menus and easy. You can design your own program. There is also a display online. It is nice and clear, but the problem is it is not real. It can't be real because it's not powerful. It's so small and simple. It's only very good for teaching. When you are using Arduino, you are not using assembly language. You will not be using assembly language. We used to use it in our time, but no, you will be using C programming language, C-like language on the Arduino. You compile it, you download the binary machine code, and it starts on the Arduino as a machine code, But you don't care. Your program is written in C. I think it's time for a break. Let's come back at like 11:05.
Ben yatayla geldim ya, ikinci sınıf dersi de alıyorum. Ve bugün değil ama önümüzdeki derslerde laboratuvarım olacak derslerde. Ya son bir saatinden ya
Hangi dersin laboratuvarı?
ortasındaki bir saat. Şöyle söyleyeyim.
Arada gelir gidersin.
Olur.
Olduğu kadar.
Tamam.
Ders notlarını veriyoruz zaten.
Evet evet. Ben de var slaytlar falan da zaten. Tamam. Teşekkür ederim. Bir de quiz, ben birinci quiz'e katılmıştım. Sonrasında adım çıkabilir yine dediniz
Çıkabilir.
ama. Teşekkür ederim.
Bilgisayardan giriyoruz da
Nereden?
bilgisayar.
Ha, ama gittiler şimdi. Öğrenciler varken bakacaksınız. Videoyu gördünüz mü?
Yok.
Bilgisayarınız var mı?
Var.
Önce ben bir videoyu göstereyim. Speed test'e giriyorum. Biraz evvel. Speed test'in initial testini geçiyorum. O kadar yavaş ki speed test'in serverlarına bağlanamıyor. Devam ediyorum. YouTube'a gireceğim. Yine giriyorum.
Hocam kaç kişi oluyor sınıfta?
100.
100 kişi.
Burada biz koymuştuk ya, ayrı bir tane ayrı bir tane access point koymuştuk. Oradan ayrı bağlanıyorduk. O zaman şifresi sadece hocalarda vardı. Bunu taktık diye onu söktüler ama bu gene işe yaramamaya başladı. Yok, çalışmıyor. Cepten bağlandım. Video gelmedi. Sefa'ya videoyu cepten kapatıp cepten gönderdim.
Fazla da düştü zaten 15.
Şimdi çıktılar.
Var da
Bağlanamıyor. Yani buna bağlanamadım. Bundan sonra YouTube açacağım, orada göreceksin. Dönüp duruyor YouTube. Yani bunun tek çaresi, çünkü biz derste kullanıyoruz. Bak buradan buna bağlanıyorum ben. Bazen de video gösteriyorum. Bunu da bağlıyorum buraya.
normal şey yok.
Normal fiş orada var. Ben oraya koymuştum eskiden. İçine bir tane küçük mikro router'ım vardı. Orada şu kolonun içine yerleştirmiştim gizli. Oradan kendime ait bir tane şifrem vardı pandemi döneminde. Oradan kendi şeyimle anlatıyordum. Sonra bu siyahı koyduk.
Evet.
Onların sökülmesi iyi olmadı.
Buraya bir hat da var gerekiyor. Versene.
Hattı nasıl bağladınız ki? Fiziksel.
Fiziksel
Çalışmıyor
olarak.
ki.
Niye?
Bunun
Dönüştürücü
var, dönüştürücü var, çalışmadı. Çalıştıramadım yani.
Çalışması gerekiyor ama
Gerekiyor işte, gerekiyor da olmuyor.
orada hat yok zaten de. Normalde Type-C bizde de var Type-C bilgisayar.
Ama ben bundan sonra yapacağım. Gene router'ımı getireceğim, takacağım oraya.
Tamam.
Kendi bağlantısından bağlayacağım. Yani ben kendi problemimi çözerim de bir problem var, ben onun için. Yani ben genel olarak yardımcı olmak istiyorum. Yoksa ben kendi başımın çaresine bakarım.
Doğru.
Bir de geçen gün biri geldi bana ofise yapmaya. Bir tane fiber fiş çantasını düşürmüş. Siz mi gelmiştiniz bana?
Ben geldim.
Bir tane kaybettiniz mi fiber?
Vallahi olabilir hocam. Çünkü
Duruyor, onu
çantada oluyor.
bir ara vereyim.
Tamam.
Çantadan düşmüş.
Muhtemelen sizin kabloları çakmıştık ya hocam.
Ha,
Orada muhtemelen bir şey çıkarırken
kutusu da var.
evet.
Bak YouTube gelmiyor.
Yok şu anda yavaş zaten hocam ya.
Ki demin daha bunlar iyisi. Yani yok işte bunun reklamları daha yeni geldi.
Ya
Speed testi.
cihazları da değiştirdik ama
Bu niye oluyor biliyor musun? çok kişi bağlanınca bunun CPU'su yetmiyor.
Evet. Yani
Şeyde de böyle. Kongre merkezinde de böyle.
kongre merkezinde.
Kongre merkezinde ben Sefa'ya o kadar dedim ya şu Türknet'e oraya da aldıralım. Bizle alakası olmadan birisi yani dışarıdan bağlansınlar. Tamamen ayrı. Getiriyordu. Yok hocam ya orada şey geçer şimdi siz kontrol ederken orası boşken kontrol ediyorsunuz. Ya da bilgi işlemden kontrol ediyorsunuz. Bağlantı yapılıyor mu? Var. Bağlantı var da millet orada ne çekiyor bilmiyorsunuz. Mesela birisi şey gösteriyor.
Orada Aruba da taktık oraya. Aruba da
Çok
yetmedi.
zor bir iş.
Aruba da
Zor.
yetmedi yani.
Şey yaptığın
Ve
zaman
mesafe de çok yüksekte ve şeyin arkasında kalıyor.
yanlara koyamıyor musun? Sağ sol, sağ
yanlara
sol.
yok. Yani dışarıdan hat çekilmesi lazım. Çok çirkin oluyor diye şey yapıyorlar. Üstlerde ve yukarıda yani. Ve önünde de şey
Aşağı
var.
koysan yani hattı alttan çeksen belki pek görünmez.
Yok hocam. Aşağıdan
Ya onu
da
mimar
olmuyor.
düşünsün ya.
Ha, evet işte
Çözümü var.
yapılmadan önce
Hayır, sonra da yapılabilir. Yani her şeyin çaresi var dünyada. Millet yoklama alıyor şeyle, QR kodla. Millet internete giremiyorlar ki.
doğru. Yani şey olunca çok kalabalık olunca yetmiyor.
Ya çok kalabalık dediğin dolu diye düşüneceksin zaten orayı.
Doğru.
Ya burada böyle durum böyle. Ben hani
Biz iletelim
gelin
yine.
çözün diye demedim ama buraya ne yapılır?
Yani iki
İşte-
tane daha ekstra bir köşeyi oraya, bunu biraz daha buraya koyduk, diğerini de oraya.
Ya aynı yere koyabilirsin. Frekans başka olursa.
Frekans ya mesafe de çok kısa.
Ha?
Mesafe de çok kısa. İki tane
Android'de
çakışır
şey var
da.
mı sizde? Wi-Fi Analyzer programı var mı?
O yok da şey üzerinden kullanıyorum.
Buradan bakıyor musun? Gösteriyor mu böyle bantları?
Gösteriyor hocam. Şu an bu bilgisayarda yok, şeyde var, tablette var da.
Ya işte onda bakacaksın.
Evet. Onda sinyalleri gösteriyor.
Yani bilmiyorum abi bu. Biz mesela video gösterecek oluyoruz. Dersin içine benim slaytlara gömülü videolar var bazen. Çalışmıyor.
Bir söyleyeyim mi hocam? Yani Mevlüt Bey şeyle
Abi ben işte ne yaptım geçen üst katta cep telefonundan bağlandım yani. Yani bu okulun içinde cep telefonundan bağlanarak ders anlatıyoruz. Hatta ikisini de cep telefonuna bağladım. Yani bunu hub olarak kullandım. Onu da Turkcell'den kullandım. Öyle çalıştım yani.
Tamam hocam biz
Ne aklınızda olsun.
Hı hı.
Ama bu bir para meselesi, şey meselesi ya da o eskileri belki tekrar takabiliriz.
projede ruh ustası mı?
Yok. Ev routerları koymuştuk ya.
Ha, bir öncekiler.
Ayrı şifre koyuyoruz. Kimseye söylemiyoruz.
Tamam, onlar
O da bir çözüm yani.
söyleyeyim hocam ben.
Premium hat.
Tamam ben söyleyeyim.
O
Konuşalım.
en ucuzu o. Öbür türlü zor.
Tamam hocam. Bir söyleyelim Mevlüt Bey'e sonra.
Bir de ben odada router koydum.
Hı hı.
4 tane makine var.
Evet.
Öyle bağladım.
Hı hı.
Router yerine switch mi koyayım? Router'da bir sıkıntı yok mu? IP falan dağıtmıyorum dışarıya.
IP dağıtmıyorsa sıkıntı yok hocam. Bazı cihazlar mesela şimdi elektrik gidip geliyor
Biliyorum,
sürekli
biliyorum.
burada. Kapanınca DSP'sini de açıyor otomatik.
Yok benim düzgün.
Mesela bir 5-6 binada karşılaştık. Tüm herkesi şey yapıyor.
Bozar.
Herkesi dağıtmaya
Bozar.
çalışıyor. İnternet tamamen kesiyor. Ona çok
Peki
rastladık.
öyle olacak adamların akılsız switch alması lazım.
Evet, akılsız switch işte biz de onlara akılsız switch
Öneriyorsunuz.
öneriyoruz. Evet. Yani olmayan yerlerde çekilebiliyorsa ilk başta hat çektiriyoruz oraya. Yani yapı işlerinden hat çektirin diyoruz. Onlar hat çektiriyor ya da illa olsun diyorsa da akılsız switch'i
Ben router koydum çünkü kendi aralarında çok fazla trafik yaratıyorlar. Bu trafik şeye çıksın istemiyorum.
Tamam hocam, sıkıntı yok. Eğer dediğim gibi
Yok kapalı.
Tamam, kapalıysa sıkıntı yok. Yarın öbür gün bir NAC cihazı alıp da onları da engellerler mi bilmiyorum
Peki
da.
engelledikleri zaman bana hat lazım.
İşte yani yaparlar mı? Şu an
Yani şöyle yapabilirler. Tek tek engellerler belki.
Öyle
İzin
olabilir.
alınır.
Çünkü yani alacağız diye bir söylenti var.
Söylediği şey sefer.
Söylenti var. Yani ne yapar, nasıl yol izlerler
Ama işte
bilmiyorum
onu
şu anda.
engellediğin zaman insanların işini engellemiş oluyorsun.
İşte dediğim gibi hocam, belki kişiye özel mesela sizin var. Siz bilgi işleme söyleyin, sizinkini açtılar gibi bir yol izlenir mi bilmiyorum.
Kaydettireceksin.
Aynen.
Çünkü bunun amacı 56-51.
Evet.
Başka bir amacı yok.
Kesinlikle.
Belki iktidar değişir.
Değişse de bu sistem değişmez sanki hocam.
İyi tamam tamam. Sağ ol geldiniz. Kolay gelsin.
Feedback alacak mı? Sadece not.
Araştırma görevlerini sorabilirsiniz.
Bu ders için 101.
Nasıl bir feedback?
Mesela bir şeyi yanlış yapmışız.
Neyi yanlış yaptığına kendin bakabilirsin.
Ha, anladım. Notlarınız dönem sonu mu görüyorsunuz?
Yo, okuyup koyuyorlar.
OBS'den.
Ha?
OBS'den.
Hayır. Temizden. Temizden değerlendirdikleri zaman görürsünüz.
Tabii ki ödevini nasıl değiştirecek? Arduino lazım mı? Arduino
Ne
tabii ki
için?
ödevini yapmak için.
Hayır, Lab 2 ödevini hayır gerekmeyecek. Ben değiştireceğim şeyi.
Yani Arduino olmadan da yapılabilecek hareket.
Lab yapılamaz da lab yapılamaz da şey yapılır. Ödevi yapılır. Önceki ödevi.
Labda da internetten bir siteden yapsak olmaz mı?
Pek olmasını istemiyorum. Çünkü aynı şey değil. Alamadınız mı? Niye?
Ya bugün deneyeceğim.
Ya bütçe mi? Yoksa başka bir şey mi? Vakit mi bulamadım?
Vakit bulamadım. Şu anda bölüm başkanı benim.
Değil. Bugün yarın. Yarın. Şu an Yusuf Hoca.
Sen benim bir ekle
Aslında Yusuf Hoca değil, Didem Hoca. Çünkü daha istifası henüz daha işlemde değil.
ekle çıkarla ilgili bölüm başkanı imzası lazım da Didem
Vekil olarak ben atarım. Yardımcısı.
çeviriyorum.
Bugün ayı kaç? 7. Section değiştirdin değil mi?
Akşam dersler vardı. Ya bir de bunu bölüm sekreterliğine veriliyor mu? Bizim bölüm sekreterliğimiz var.
Var şu anda kapıda bir isim var. O ismi araştırma görevlisini bulacaksın. Ona vereceksin.
Hocam yeni laboratuvar, Arduino laboratuvar dosyasını ne zaman yükleyeceğim?
Ödevi mi?
Evet, Prelab Homework ödevi.
Prelab Homework ödevini değiştireceğim ben. Bu akşam yüklersiniz. En geç değil de yani.
Yeni dosyayı siz bu akşam yükleyeceksiniz.
Ben yeni dosyayı yükleyeceğim. O çocuklar prelab yapmamışlar, lab'ı koymuşlar. Lab konmayacak. Prelab başka olacak.
Tamam, o lab'ı lab'da mı yapıyorsunuz?
Lab'ı lab'da yapacaksınız. Belki birkaç şey daha isterler ama. Yani ona hazırlık için bir ödev vermeleri gerekiyordu. Lab'ın kendini vermişler. Hafta sonu şey vardı, işte sen biliyorsun. NASA'nın Space Apps Challenge'ı vardı. Hepsi, yani büyük bölümü lisede kodlama yapmış çocuklar, yapmaya çalışan. Evet arkadaşlar, kıyma makinemiz geldi. Buna iyice bir bakın. Konsantre olun, dalın gidin. Tamam, baktınız. So, this is the same. The program is controlled by two special purpose registers, program counter and instruction register. What it is and move on. What it is, move on. And that one cycle is actually made up of understanding it, getting it, understanding it, and executing it. Getting the instruction from memory, understanding it, and doing it. So we call it as fetch, decode, execute cycle. Tekrar kıyma makinesine geri dönün. The first one is retrieve the next instruction from memory as indicated by the program counter and then increment the program counter. Then understand it. Step 2, decode the bit pattern in the instruction register. Step 3, perform the action required by the instruction in the instruction register. All in one cycle. Get, understand, execute. Get, understand, execute. So that keeps repeating. And each instructions are executed one by one. And if there is a branch or go to, you will immediately go to a new address indicated by the program counter, because go to instruction actually changes the program counter. Go to changes the program counter. And this meet machine in the next cycle goes to the next the other address because program counter is now changed. So at each cycle it goes to the address where the program counter shows. Program counter shows 5. It goes to the 5th location and gets the instruction. If the program counter shows 20, it goes to 20 and gets the instruction. And at each cycle, it is automatically incremented by 1, or sometimes 2, 20, 21, 22, 23. So that is next line in the program. In this architecture, it goes 2 by 2, because our instructions are 16-bit and location addresses are 8-bit. So each instruction takes 2 spaces. This is the first space. This is the second space. That is the code, opcode, register number, and the address, generally the address. Which register? Which memory? What? Is that clear? So, for example, A0 A0 is first taken to program counter. Then as you rotate this 15, 6C goes here. 15, 6C. Then we understand what 15, 6C is. Control unit automatically adjusts flaps so that arithmetic logic unit adjusts itself, and at the end of the cycle the number in 6C, somewhere here, 6C, number in 6C is loaded into register 5. So register 5 is loaded with number in 6C. At the end. In the next cycle we get A2 here, and 1660 is taken. 1660 is taken here, understood, executed, which is 660 is put here. 5056.
I didn't understand that.
Add 5 and 6, add 5 and 6 and put the result into 0. Okay. Then 306E store where 6E. Then C000 stop. That is what you have in the memory. And program counter increments 2 by 2, A0, A2, A4, A6, A8. The increment step is determined by the architecture. This machine increments 2 by 2 automatically because it is 16-bit instruction type by design. This 1560 goes into instruction register. 1660 is there. Program counter is A2. But the next instruction, 1660, is loaded. And so on. Any questions? The arithmetic logic unit can make AND, OR, and XOR. XOR is interesting because it allows us to make subtraction using addition. We have rotate, shift, circular shift, logical shift, arithmetic shift, different ways of shift. What are those shifts? You have a number, binary number. For example, when you logical shift left, 0 is inserted to the right. And this one drops, is erased. So everything moves left, the bits. But if it is arithmetic shift left, you read the first value from the right, insert that as a new value. So you repeat the value that is already there. In some other shift, you take this, put it on the right. It becomes rotate. And there is also rotate right or the opposite direction. So rotate left, rotate right, arithmetic shift left, logical shift right, arithmetic shift left, logical shift left. So there are multiple types. And arithmetic operations, add, subtract, multiply, divide. Our CPU, the simple CPU, doesn't have that. But many normal CPUs have that. Add, subtract, multiply, divide is available. Also, there are 2's complement numbers, floating point numbers. So floating point multiply, 2's complement multiply. There could be multiple instructions doing the same thing for different types of numbers. This is, for example, the rotation. The rotation to the right. Everything will move to the right. This one will go to the right. This one will go here. So at the end, it will be this one will be this one. Everything moves to the right. And the rightmost goes to the left. That is what we say rotate right. Why do we need that? Why we might need rotate right? There might be many reasons. One is these bits might be connected to external world. For example, this could be connected to a switch. So you are trying to understand what the switch status is, as in the homework in the lab. You are trying to read that switch. So you may need to rotate left 1, 2, 3, 4, 5 times and check the sign of the number. If the number is negative number, then that bit is 1. If the number is positive number, that bit is 0. So that is one thing to reach that. There are other methods. The other thing is when you are rotating left, if it is arithmetic, it means multiplying by 2. When you are rotating to the right, it means dividing by 2. Shifting left, shifting right is associated with multiplying and dividing. You will learn over time, so don't make it too complicated for you. And this memory should talk to the CPU. But there could be other things in the environment, such as disk drive, floppy drive, this memory chip, the other memory chip. How many memory cards in your computer? If you have a desktop computer at home, you usually have 2 cards, 2 memory slots, and 2 different memory units in that memory slots. And on the card, you may have multiple chips. Each chip is, for example, if it is 8 gigabyte RAM and you have 4 chips on it, each chip is of 2 gigabytes, 2 gigabyte, 2 gigabyte, 2 gigabyte, 2 gigabyte, right? 8 gigabyte, another 8, 16 gigabyte. So each of them is separate. So there must be a way of using this bus collectively, like people using the same tea house in the street. Same tea house can serve multiple stores for bringing tea. As I said, in the older times, there was a rope from one end to the other end of the street. You go out, shake the rope, and the bell was shaken. The bell was actually the goat's bell or the sheep's bell, taken from hardware store. Koyunlar veya ineklere taktığınız çıngıraktan. So if it rings, then kahveci was going out, the tea guy was going out, and you get face to face, and you say 2 tea. This means probably soda. This means tea, and this means coffee. So by sign language from one end to the other end of the street, you were able to communicate. But the initial part, the interrupt, was provided by the rope and the bell. You don't have to go there to ask for the tea. Later it is replaced by diaphones, electronic ones, and there were wires, and there are buttons outside outside of the store. It is installed by the kahveci, okay, the tea man. And you go out, just go out the shop, press the button, it beeps, the kahveci responds. What do you want? And say, I want 2 tea. He asks, where? Because he doesn't know who is calling. You have to identify yourself. Terziye 2 çay. Okay? Then he knows where Terzi is, etc. So that kind of negotiation is needed. Recently, they use wireless walkie-talkies. They distribute walkie-talkies, and you do the same thing through the walkie-talkie. You press the walkie-talkie and announce your request, etc. Everybody hears it. So if you don't use the walkie-talkie as a store owner, you turn it off because you will hear other people calling for tea. So that is a way of communication. Usually, in order to communicate, there must be a controlling mechanism. We call them controllers. Some communication is done through the ports. Some communication is done through memory. When you write to the memory, it might mean some output. Or you may have special instructions, say write out instructions. You need to call that instruction that specifically writes to the ports. So that is port-based communication or memory-mapped communication. Memory-mapped communication is more advanced. It is more advanced, elegant, and also simple. It's easier to understand. You don't need additional instructions, additional modifiers. You write to the memory, and it becomes output. You read from memory, it becomes the input. It's outside. Okay. So typically, this is the computer, and in order to understand that this is the computer, you need input and output. Okay. There is also similar explanation for understanding of the universe. I mean, why are we here, who we are, etc., those questions. So if there is no input and output, you didn't know that you existed. So due to the input-output that we are having now with each other, we realize that we do exist. So this is the CPU, connects to, writes to memory, and there are other players. These other players interact with the memory cells, and CPU uses the memory in order to communicate. There are no other channels. And this is perfectly fine. So the purpose of the memory is not only to store program and data, but also then to communicate with the external world, to make input and output through the memory. In the port-based communication, you have in and out instructions, special instructions with operands. You only have to use that instructions, whereas here we have load and store, just like we are doing with the memory read and write. We are using the same instructions. Here you need different instructions. You have to learn additional instructions. You have to adjust your compiler, C compiler, Java compiler, Python interpreter, whatever, to work with these input and output, then it will work. This input and output with the bus into the bus, output to the bus, and these are connected through the bus, it's also possible. This is the KVG example. I have the, okay, this is the KVG structure. The rope was like that. There were pieces of rope hanging down. And KVG is here. And the bell is also there. So you just go out, shake this, okay? And the mechanical energy is transported with the rope, and the bell rings on the other end. And you both go out and see each other and negotiate. But this street is used by all the players. So this is bus. That's the main street. Multiple controllers. But only two can talk at a time. If there is a tea shop and a hamburger shop using the same structure, this is the hamburger line and this is the tea line. Once you are shouting with the hamburger, the others should wait a little bit. Okay. Similarly, this is the diaphone, recent one. Similarly, in the buses, what do you do in order to get off? You press the button, and the button notifies the driver that there is going to be some person who is going to drop off, get off, and he prepares himself accordingly. In the older times, we had, when I was student, the Istanbul municipality had Leyland British buses, which are automatic, and their notification mechanism was with this rope. There was a rope hanging down through the right window and the left window from the beginning to the end. And unlike today, everybody was able to sit, so it was like a regular bus, but in more simplified. So 2 on the right, 2 on the left, and 1 corridor in the middle, and 2 ropes next to the windows. So if you are going to get off without getting up and approaching to the door, you just pull the rope. When you pull the rope, there was a switch at the very front. When it was pulled, switch was connected to the electric bell. Electric bell was rang, and there was a sign says duracak, it's going to stop, and the driver was notified. So it was also bus structure. There was a rope going from back to front. Everybody can access it in parallel. Same kind of approach, but without the bell, there was a switch connected to the rope. So it was more advanced. Bir de şey var ama onun örneği başka. Onu da zamanı gelince anlatırız. Apartmandan sepet sallandıran teyzeler var bakkala. So we have CPU connected to main memory through the bus, and we have peripheral device. Peripheral device is connected to the memory with a controller, with some of the memory cells. How do you do it? Şurada kapı pencere açık. How do you do it? This is memory. Are they going to be conflict? Because memory also has chip. The answer is no, because when you are connecting this controller, the bus is not only the data, but also shows the address. So each memory cell has an address, like A0 to FF. Each of them is connected through another wire. So when I am trying to read A0, part of the bus indicates A0, meaning that I am reading A0, and this memory chip automatically is connected to A0. If I am reading A2, this data bus CPU extracts A2 to the data bus, and A2 is connected to data bus. So wherever I am interested, that part of the memory is connected to the data bus. I indicate my intent with the address bus. So bus is actually address bus plus data bus. And there is also control bus, such as indicating whether I am reading it or writing it. Few more lines are control buses, read, write, or strobe, etc. There are some wires along with it, indicating what am I doing. Each of them has address, and this controller is connected to certain part of the addresses. If that address, for example, C7, if C7 is selected, memory is deactivated, controller is activated. So for that address, C7, memory chip is deactivated, controller is activated. Then I can read. It is again memory address, but actually the data provided by the controller. Let's pass this another example taken from internet. When you have multiple buses, it looks like this. You have a CPU, North bridge, South bridge, PCI bus, front side bus, memory bus, AGP bus. These are typical configurations for the CPU PCs. As a computer engineer, you don't pay attention to these things unless you are interested in hardware for the rest of your education. Generally, we are more interested in the layers and the things on top of the. So, if your friend is going to ask which computer I should buy, you probably will not know, because that's a different story. I don't know which computer is good. If you are interested, yes, you will, but as a topic to be taught in the university, it is not related. If two people shouts on the same bus, on the same street, chai, hamburger at the same time, we call it contention. So we detect the contention, we stop and try again. It was one algorithm. So we have to organize, or we have to develop a mechanism. We have to pull something else, If that is pulled, nobody else could start. So whoever does it first keeps going until it finishes. So that's one also solution. So the solutions are not that easy. If you go into detail, you may say, what if those two people pulls the control signal at the same time? So that can happen. So there must be a small program to understand it and also resolve it. So contention resolution protocols. When communicating with other devices, you can have direct memory access thing. As we see, read from memory, operate, and write. Some instructions may take, in complex CPUs, some instructions may take multiple instruction cycles. Multiple cycles is required, such as multiply, divide. It may take multiple clock cycles. For that reason, one guy said, can we use the memory with another chip while CPU is busy? The answer is yes. While CPU is doing something, at the same time, when the CPU is not really needed, I can access the memory at the same time. That is called direct memory access. For example, the graphics card accesses the memory while CPU doesn't. So they interleave. Graphics card controller memory access. Laptoplarınızda ne yapıyorsunuz hakikaten? Baksanız iyi olur. Benim konsantrasyonum bozuk. Şeyde firmalara eğitim veriyorsun mesela. Yani toplantıya gidiyorsun. İşte 20 kişi var orada mesela. Herkesin laptopu açık. Herkes e-mailini şey yapıyor. Eğitime zorla gelmişler. Aman gidin o zaman yani. So while the CPU is not functioning, direct memory access controller can help. Not this one. Okay. So when the bus speed is not sufficient, CPU is fast, but data transfer is not as good. So that slows down the whole operation. That is what we say von Neumann bottleneck. And for artificial intelligence, it is very memory intensive. Because the neural network operations require this part of the memory, this part of the memory, almost at the same time, because you have to multiply this and this right here. 16 gigabyte or 64 gigabyte. So a lot of memory intensive operations, arithmetic operations are required constantly. So graphics card architectures are more suitable for it.
CUDA course, right?
CUDA is a programming language. Library.
Oh, I mean, on the GPU, there are CUDA cores.
They say CUDA because it is NVIDIA, but it doesn't have to be NVIDIA. For example, I use Apple. Apple has its own GPU cores. The advantage of that is those things are their memory access is optimized. So when you have very fast access to memory, and the speed between CPU and memory is similar, you can do a lot of graphics intensive and artificial intelligence intensive operations. And what CUDA cores, he said, provides that. Memory speed and CPU speed is very close to each other because they are physically close to each other. And I am sending you a letter expecting to give my money back. You owe me 1 million Turkish lira. I'm sending an email, for example. 1 million lira. Give it back as soon as possible. And time passes, nothing comes back. You send again, no answer. And suddenly, a couple of weeks later, you saw the guy on the street. Okay? And you say, I sent 2 emails, give me my money. And he says, I didn't get it. When did you send? He said, I didn't get it. So you don't have anything to do. Therefore, when you are communicating, there must be a way of confirmation in between. Whether the other parties taken the data so that you are sure that it is taken. Sometimes you send it, but he is not ready. So it is actually gone to the empty space. It doesn't go anywhere. But for reliable communication, you have to make sure that the message is actually data. For example, when you are writing from CPU to hard drive, the message is data. You shouldn't lose any of it. So you have to be sure. Therefore, verification mechanism is required. That's what we say handshaking. That's the bus button. To solve this bus bottleneck, you may have to create additional links to make it faster. Yeah. Direct memory access, or there was another example. Direct memory access while CPU is busy. Other controller can access the memory. How is it? If you have intimate relation with the coffee guy, you can go to the coffee shop, make your own tea, and come out. The tea guy is doing his own job because you know him so well. He doesn't bother. You get your own tea, put the money back, leave the money there, and go out. So it actually speeds up the operation of the coffee shop because the coffee guy is doing something else, like maybe cleaning the dishes, etc. Okay? Early yerler de tükeniyor yavaş yavaş. Bunlar iyidir. Okay. So when you are kaç kişi tarlada çalıştı? İyi. So when you are loading something to the truck, you actually send it. The other guy has to catch. These guys are relatively slow, but this is the picture I can find. If you don't pay attention, you drop it. So you have to be synchronized. And in order to be fast, you have to be synchronized. Otherwise, if you are slow, these guys should say, Ali says, send me please. Veli, here you go. Send, take. Send, take. So otherwise, you may drop it. The first, these are not young people. If these are young people, powerful young people, they keep sending it without saying anything, right? So if the speeds can match, it is successful. Sometimes, for example, if this guy tries to smoke once, and synchronization is collapsed. So couple of melons, watermelons, may be lost. If you can live with it, that is the good choice because it is very fast. Otherwise, you need handshaking. This is what we call half handshake. Why? Because Ali said, send me please, Veli said, here you go. But at the end, Veli doesn't know whether Ali is successful or not. Ali may drop it. Veli doesn't know. In this case, they have eyes, but in computer sense, they don't have eyes. It's only talking. Another example. Things keeps coming. You keep putting it, the other guy is taking it. But since there is a line here, it sometimes allows you to be asynchronous little bit. You can smoke your cigarette for a couple of seconds and continue, no problem, because this is moving slowly and can hold multiple watermelons. Here you have multiple watermelons, not one. With this one, you only have one. That goes here. With this one, you have multiple coming. So if you put another one, the receiver doesn't care. That thing is called as buffer. Okay, it has a length, it has a capacity, like 10 watermelons, 10, 7, 5 watermelons, up to 10. It's okay. If it is 10, it is full, you stop, because there is no place to put it. It keeps moving, you put another one. So you are actually, in this case, you are interacting with the buffer, not with the other guy. There is another guy here. Assume that these are the things that I can find. Assume that this is the sending guy, this is the receiving guy. They don't have to negotiate each other. This guy negotiates with the roller. This guy also negotiates with the roller. So that is the buffer. Has variable capacity. It has maximum capacity, but also more than one, so that it can shrink and grow. With the full handshake, guaranteed delivery, send me please, here you go, thank you, no problem. So this case is full handshake, tak, tak, tak, tak. So with the binary signal, 1, 1, 0, 0, as the handshake line, in both ways. That is what we say full handshake, half handshake. Also there is stroke method. This is quarter handshake. Take it, take it, take it, take it. The receiver doesn't say, send me please, nothing. Take it, but when the receiver should monitor the stroke, this guy should monitor the stroke. When he hears take it, he should turn, it's coming. He may catch, he may not catch, God knows, but at least Veli says, take it. Okay? This communication examples I have given are serial communications, one by one. If each of them is one bit, one by one. If you have multiple people sending, then it is 8 guys here, 8 guys here. So transferring in parallel, that's called parallel communication. In the chip sense, you have multiple bits. Your Arduino, for example, is something like this, and a clock. On one side, 18-year-old young, powerful guy. On the other side, 85-year-old grandfather. Speed doesn't match. In order to successfully transfer data, you need to synchronize timing. When you share timing, if it is parallel, then it works. This is parallel. Clock is interesting. For example, have you seen rowing machines, rowing boats with multiple people? Kürek takımı. There is a guy who is in charge of the guidance, and he instructs, and the people shouts like hey, hey, hey, and at the same time they synchronize themselves. Otherwise, they are not synchronized. In the older times, in Viking ships and British ships, or ships that were propelled by human power, for example, one ship can contain 100 rowers. 100 people are rowing at the same time. In order to synchronize it, there were drums. At each drum, they row once. At each drum, they row once. Otherwise, they are in trouble, asynchronized. So they also adjust the speed by changing the tempo of the drum. That's parallel. In series, you also send clock. You may play music. So at each beat of the music, another watermelon comes. That's a help in synchronization. So it's a clock. Otherwise, you need throwing data, request and acknowledge. So this is handshaking. Put data, please take, got it, full handshaking. Without handshaking, you may have clock. This is possible. If you share the clock, same powerful guys, same music is playing, then it can work. But without that, if you don't send clock, you need to handshake. Oh, this is called, when you share clock, we say synchronous communication. If you don't share clock, we say asynchronous communication. Synchron ve asynchron. In a security camera, you have usually time here, and it's changing. Why is that so? Because the security guy knows that it's showing the current data. If you don't show the time, all you will see was an empty room. It could be yesterday's recording. And in the films, that's what they do. They insert a previous day's recording to the stream, and they can steal whatever they want because the security guy was watching the day before's video. But the date is different. They don't realize. So you need to understand that data is coming and keeps coming. So how do you understand data is coming? There's a line in the kahveci example, in the team man example. It bells. So bell rings, then you realize that data is coming. But in binary, how do you know? 0, 1, 0, 1. If it is all 0, 0, 0, 0, 0, 0 volt, is it 0 coming or nothing is coming? Is it dead? If I cut the line between sender and receiver in the watermelon example, if Ali is dead from heart attack, no watermelon is coming. Does that mean watermelon is coming or Ali is dead? Which one? So there must be a mechanism to understand that data is 0 or no data. Is it 0 or no data? So to do that, one solution is to send also clock. When you receive the clock, hey, hey, hey, hey, then you understand that we are connected. You are not dead. We are connected, and actually nothing is coming. If something is coming, it will come. But sometimes clock is not sent. So coding like Manchester coding, different types of coding is developed. Instead of one as a 5 volt, 0 as a 0 volt, edges are important. Going up is 1, going down is 0. So if there is a change in voltage, it is the information. This part is not the information. The information is the change. Because that's how I understand that the other part is living. If it is the same, maybe it is the previous value for hours. But if there is a change from high to low, it is 0. From low to high, it is 1. So for each byte, this is 1. This is down Manchester, this is up Manchester. 2, for example, this one. 1 is going up, 0 going down. 1 going up, 0 going down. Another 0, up, down. So this down is actually 0. So these methods enables us to notify the receiver that there is change in the sender side. It is not that easy. And bits per second, kilobits per second, megabits per second. If this b is small, it is bit. If it is big, it is byte. So it's 8 times difference. Bandwidth means maximum available rate. Okay. Okay. So when I am writing a program in assembly language, it is hard because programs take too long and it is less closer to the human language. What I do is I develop a language, higher level language like C or Python or whatever, to translate them to opcodes. Typical programs contain these kind of statements: if, while, etc. This is from Python. We have functions. We encapsulate frequently used parts in order to write them again and again and again and again. What I do is, it's a well-defined thing. I write it as function, I call it. What is calling? Program counter jumps there, executes, and comes back. So that is what calling means. What is the argument? Argument is the value that goes into the function. Like add x, y. X and y are arguments. So again, when I say side A equals 3, floating, this is the assignment. If you see side A again, it might be different because somebody else might change it. So here you can say side A is equal to 3. Then you will say side A equal to 10. So 3 is gone. It cannot be equal to 3 and 10 at the same time. The last assignment is always valid. Usually we have print word in most languages. So print or println, print something related, write out, write-ln. These are the output instructions, and inputs are collectively input most of the case. These are examples and the output. These are not important. I think I'm done with it. Now for the quiz, I'm going to choose Yok, var. Okay. Okay. İkinci kez çıkan var mı?
bunu yapmanın daha şans artıyor mu yoksa? Geçen bana şans
Alakası yok. Hiçbir alakası yok.
bana şansı çıktı.
115'ten seçiyoruz zaten.
Robotistan'dan alamadım. Stok bitmiş de. Ya başka bir internet sitesinden ya da yazıcı ondan alacağım. Şimdi böyle kesin gerekli olan karşılayacağım bir şey var. Yani hemen hemen aynı oluyor başka bir sitede de.
En ucuzunu al. Minicik bir tane breadboard. Minicik bir tane breadboard. Bir iki tane led varsa yeter. Bir iki direnç.
Hocam şimdi bu memory access sırayla oluyor ya. Yani bu şey mi demek? Aynı anda benim Wi-Fi'm çalışıyorsa bir yandan işte müzik çalıyorsam bir yandan başka bir şey yapıyorsam bütün sürücüler hepsi sırayla mı?
Sırayla.
Yani onu hissetmiyoruz ama biz çünkü çok hızlı olduğu için. Ama cihaz CPU sırayla ekleşiyor.
Hocam bir şey soracağım. Ders dışında, ders hakkında sorular hangisini yaparsınız sorabiliriz?
Çarşamba günü ama asistanlara da sorabilirsiniz öncelikle. Arasında gördüğünüz 4 tane asistanımız var. Her zaman sorabilirsiniz.
Ya asistanlara sormakta sıkıntı olmuyor değil mi?
Hayır, esas onlara sormanız gerekiyor.
En son bir seviye.
Evet, onlara sorduğunuz cevap alamadıysanız bana gelin.
Tamam, teşekkür ederim.
Biz birinci yılda yapmadık çünkü
Tamam.
sistemde değildik. O yüzden
Tamam. Sonra yaparsınız.
tamam ama şey çıkmıyor zaten.
Yani
Yani öyle biz
yapacak bir şey yok.
onu yapabiliriz.
Hiçbir şey yapamazsınız. Diğer ödevlerinizi iyi çalışırsınız.
Tamam.
Tamam.
Ve şey slide.
İnternete koyacağım.
Tamam. Bugün ya da hafta.
Kitabı indirdiniz mi?
Evet.
Kitaptan çalışmaya devam ederseniz yeterli olur.
Tamam. Science and Technology için.
Ona geliyor musunuz?
Evet.
Peki, ona da mı gelmediniz ilk derse?
Geldik.
Tamam.
Ama kitap hangisi?
Kitap yok, slaytlardan. Dersi dinleyeceksiniz orada.
Tamam. Ama siz slide'lar
Koyacağım.
tamam. Kolay gelsin.
Yani hocam ders kayıtlarını Teams'e mi yükleyeceksiniz?
Yok, Teams'de